Hey everybody. If you're watching this video, hopefully on, I suppose either on Tuesday night or Wednesday, depending on when I get this posted or edited and posted. But my plan for this is to just go through a few different examples. I went through and there's a lot of really wonderful problems in this review assignment. In fact, I think it's safe to say that everything that is on the test is on this review assignment in some form. So if you can do everything here, then you're going to be just fine on the common exam. Like I said, I just went through and picked out some problems. I'll just start at the beginning. I looked at number 5, and this jumped out at me as a problem that we could do two different ways. But the easier way of doing this is to apply some properties of logs first. Don't just take the derivative as is. Whenever you've got y is the natural log of some function, if that function is kind of complicated, we can usually simplify it. I know the log of a product can be broken down to be the log of the first thing plus the log of the second thing. And in this case, it gets even better because the natural log of e to the x, well, natural log and the natural exponential cancel each other out, so that's just x. And then the natural log of x squared, I've got natural log of something raised to a power. So you can bring that power down to the front. So I haven't even started taking the derivative yet. And this is now 2 times the natural log of x plus the natural log of e to the x, which is just x. And so I've gone from something that's a product rule inside of a chain rule inside of a log function to just a simple log function and x. So my answer on this one is just that the derivative is 2 times the derivative of the natural log of x, 2 times 1 over x, plus 1. And if you do this the hard way, if you say the derivative of log of something is 1 over the something times the derivative of the something, it works out, and you got a lot of simplifying that you can do to get it to look like that. But obviously simpler to do that. Question number 9 jumps out at me as a unique case where I have a function raised to the power of another function. Notice it's not x to the cosine of x, but it's the natural log of x to the cosine of x. So this property that I used back here, when you got log of something raised to a power, that's different than the entire log raised to the power. And the way that we saw of doing this was pretty recent. We used something called logarithmic differentiation. That says, I don't know how to do the derivative of a function raised to the power of a function. So I'm going to apply the natural log to both sides. And I know this gives us something that's even more complicated, but now we can apply that property of logs that says log of something raised to a power. Now I can bring that over into the front. And now I've got a function times a function. And this nested log is a little bit complicated, but well, nothing that we can't handle, right? So I've got a product rule over here on this side. I've got chain rule nestled inside that product rule. On the left side, because I've got a function of y now, when I find the derivative in terms of x, if I find dy dx, we're doing implicit differentiation. The derivative of the natural log of y is 1 over y times the derivative of y, I'll call it dy dx. And the derivative of the right side, I've got product rule. And so I will do cosine, the first, times the derivative of log of x. The derivative of log of something is 1 over the something times the derivative of the something, in this case the stuff inside, is natural log of x, and the derivative of the natural log of x is 1 over x. Halfway done with product rule. I've got the first times the derivative of the second plus the second times the derivative of the first. The derivative of cosine is negative sine. Now, a little bit of simplifying, I can combine this together to make a simple fraction. Since I've got a negative there, I might make it minus that stuff. And also, I'm going to multiply both sides of the equation by y to get dy dx in terms of y. So after I do that little bit of simplification, I'll have y times, I'm going to use a big bracket here because I've got a lot of stuff. Cosine in the numerator, and natural log of x times x. I'll call that x times the natural log of x, just to avoid confusion so it doesn't look like natural log of x times x. And then I'll make this minus because I'm subtracting that sine term. And I guess I'll just call that sine of x times the natural log of x. And then I started, my original statement of the problem was y as a function of x, so my derivative should also be a function of x. Fortunately, y is just natural log to the cosine. And so I'll just replace that y with the original function that it was equal to. And then I don't think I have any more simplifying left to do, so I'm just recopying that same stuff. And there we go. A little bit more complicated, but like I said, nothing that we can't do. And could we simplify distributing? I don't think so. It's not a simple log multiplied. Yeah, I think I'm just going to leave it as is. Question number 11, the reason I chose question number 11 is because I wanted to just jump off of the page at you. When you look at this and you see these things are multiplied, this is instantly a product rule problem. The derivative g prime will be the first times the derivative of the second. The derivative of e to the x is just e to the x, plus the second times the derivative of the first. You might want to think of that square root of x as x to the 1/2 power. And so its derivative is 1/2 x to the negative 1/2. And then a little bit of simplifying that I can do here. I can say that this is the square root of x times e to the x. I noticed another e to the x over here, so maybe I'll factor out that e to the x. I've got a 2 in the denominator, and x to the negative 1/2 is the same as 1 over x to the 1/2, or 1 over the square root of x. And then maybe I factor out an e to the x. Yeah, tempted to do more simplification here. Maybe I'll just factor out that e to the x, and I'll be left with the square root of x plus 1 over 2 root x. Yeah, tempting to combine these two into one, but I think I'm getting ahead of myself if I start going in that direction. Moving along. All right, continuing on, a couple more problems for us to look at. Number 14, we just have a relatively complicated chain rule problem. 3x inside an e to the x with some other stuff inside a square root of x. Can't do any simplifying first, so I'm just going to say the derivative of the square root of something is 1/2 times the something to the negative 1/2. I repeat, the derivative of the square root of something is 1/2 times the something to the negative 1/2. I'm not thinking about the derivative of the stuff inside yet. Well, until now, multiplied by the derivative of the stuff inside. So now I'm just looking at this part of it, the derivative of 1 plus 2 times e to the 3x. Well, derivative of 1 is 0. The derivative of 2 times a function is 2 times the derivative of the function. And the derivative of e to the 3x is e to the 3x times the derivative of the 3x. Now the stuff inside is that 3x, and so its derivative is 3. So the first stuff inside is this 1 plus 2 e to the 3x, and then the derivative of, well, a constant plus a constant times e to the 3x is just 2 times derivative of e to the 3x, which is e to the 3x. I mean, the derivative of e to the whatever is e to the whatever times the derivative of the whatever. In this case, the stuff inside is 3x, so its derivative is 3. And then just a little bit of simplification here. I've got a 1/2 times 2 that can cancel out. I've got all of this stuff to a -1/2, so I'll throw that in the denominator. I'll keep this 3e to the 3x in the numerator. And 1 plus 2e to the 3x inside that fraction. Let's see, question 21. What jumps out at me here is that I've got a function times a function. This is product rule. And then this part of it, this natural log of the inverse tangent, will be a chain rule. So that'll be the tough derivative. We'll save that for the end. I'll start with the derivative of the first. That's just 1 times the second. I'm going to write this as inverse tangent of x. So the derivative of the first times the second plus the first times the derivative of the second. Here we go. The derivative of the natural log of something is 1 over the something. Times the derivative of the something. Let's see, the derivative of the natural log of that stuff is 1 over that stuff times the derivative of that stuff, and the derivative of that stuff, the derivative of inverse tangent is 1 over 1 plus x squared. Remember, you will have a formula sheet on the common exam, so don't waste too much time memorizing. Spend your time practicing this stuff. And then if I can simplify, I guess I've got a lot of 1 times 1 times 1. Let's maybe write this as the natural log of the inverse tangent plus, in this fraction, looks like all I have in the numerator is x, and in the denominator I'll go with 1 plus x squared times inverse tangent of x. And I don't see any more simplifying than that. Question number 27 is asking us to find the equation of a line that is tangent to this curve. One of the reasons I wanted to do this is to talk about when we plug in that 2, 1. And there's a couple ways of thinking about it. But step 1 is take the derivative. I've got x's and y's all over the place. So I'll just have to remember when I take the derivative of a y term, I'll have to tack on that dy dx. Derivative of x squared is 2x, no problem there. Derivative of 4x times y, I'm going to call that 4. Derivative of 4x times y plus 4x times the derivative of y, dy dx, plus the derivative of y squared is 2y times the derivative of y, dy dx. And the derivative of 13 is just 0. So again, derivative of x squared, this is product rule, derivative of 4x times y plus 4x times the derivative of y. And then the derivative of something squared is 2 times the derivative of the something. The something in this case is just y. Derivative of a constant is 0. Now, one way to do this would be to go through and do a whole bunch of algebra, isolate these terms, subtract, divide, get this as dy dx equals some function of x and y. And I'm not going to say that's wrong, but for a problem like this, where I only want to find the line tangent at this point, I'm going to plug in that point and then solve what's left for dy dx. And it's just going to be a lot simpler to do that than it would be to go through the process of finding dy dx in terms of x and y. Now, if this problem just says find dy dx, and it doesn't say anything about an equation of a tangent line, find dy dx. I don't know what the answer is, but you could find it very easily. I'm guessing some of you would want to do that, and that's fine. Like I said, isolate the dy dx terms, factor out the dy dx, divide by what's left over, and come up with that. But I am going to plug in the point 2, 1 in place of x and y. So I'm going to have 2 times 2 plus 4 times 1 plus 4 times 2 dy dx, I don't know what that is, plus 2 times 1 dy dx equals 0. Okay, at this point, whoops, I am picking up after a hour-long interruption for a review session. which doesn't matter to you as you're watching this video, but I left off having plugged in my x and y values. At this point, I just have 4 plus 8 times dy dx plus 2 times dy dx equals 0, which means I've got 8 plus 10 dy dx's equals 0. Think of that dy dx like a big X. 8 plus 10x equals 0. I'll subtract 8 from both sides of the equation and divide by 10 to get dy dx is off the bottom of the screen. Let's move it there. Is equal to, let's see, negative 10 over 8, which reduces to negative 5 over 4. Now, if we had solved for dy dx, if I had taken this expression and moved all the dy dx's to one side and kept all the other terms, factored them out, divided over to the other side, I would have an expression here. And if I plugged the point 2, 1 into that expression, I would still get negative 5, 4. We would just have to do a little bit more writing, a little bit more algebra with variables instead of algebra with numbers. Either way, we get to this point. That is the slope of a tangent at the point 2, 1. So all I have left to do is to write down my equation. Y minus the y value equals my slope times x minus the x value. And so that is the equation for the tangent line at the point 2, 1. A couple other questions that I wanted to take a look at. I'd like to take a look, that's easy for me to say, at question number 30, at least parts, I think this is parts A and C. This is one where we have the table of values. So instead of copying down the whole table, I'm just going to refer to that when we need to. But in the meantime, we're given that this function p is x cubed times g of x. And so when I take the derivative, I've got a product rule, this thing times that thing. So we'll go with the derivative of x cubed times g plus x cubed times the derivative of g. And I don't think we can simplify that a whole lot. So if I want p prime of 2, I'll just go ahead and plug in 2 in place of x. 3 times 2 squared times g of 2 plus 2 cubed times g prime of 2. And so the things that I need to look up from the table, I'll need g of 2. And as I look at the table, g of 2 is 4 plus 8 times g prime of 2, and g prime of 2 is 2. And so I've got 48 plus 16. 48 plus 16 would be 64. So this is what a product rule problem would look like. And then part C, and I guess I'll refer to part B also. Part B is just a quotient rule, same idea. But there's no chain rule mixed into it. So it's just quotient rule, but I'll leave that for you to do on your own. Or come to one of our study sessions on Wednesday and find out. But I'm going to take a look at part C. C is f of the square root of x. So when I find the derivative of f of something is f prime of something times the derivative of the something. Well, the something, the inside stuff, the inside function, in this case is the square root of x. You can think of that as x to the 1/2 power. So its derivative is 1/2 x to the negative 1/2. And then I'll just rearrange things a little bit. F prime of the square root of x, I've got a 1/2. So I'll throw that 2 to the denominator. I've got x to the negative 1/2. That's 1 over x to the 1/2, or 1 over the square root of x. And so if I want to know what c prime of 4 is, I will now, just like I did for all the other functions is plug in 4. I need f prime of the square root of 4 and 2 times the square root of 4. F prime of, well, I suppose the square root of 4 is 2. And 2 times 2 will reduce to 4. So it looks like the only thing I need here is f prime of 2. F prime of 2 is -1. And 2 times 2 is 4. So that is the value of c prime of 4. And there we go with that problem. I looked through a few of the questions from the book, and a couple stood out to me as ones that I wanted to include in this video. This is question number 65 from the section that involves page 206. We're given, instead of a table of values, I was looking at that one after we looked at the problem with the table of values. We had to look up different things on the table to find what's the value of the derivative, what's the value of the function. And there will be some cases where you've got, instead of a table of values or an expression for a function, you just have a graph. And so we're going to have to find what are the values of the function, what are the values of the derivative of these functions, given this information. For the problem in the book, this is color-coded. One of these is red and one of them is blue. Mine are both blue just because that's the color of pen that I've got. But hopefully we can see the F graph looks like that. The G graph looks like that. And of course, you've got your book. We're given that this U function is F composed of G, F of G of X. And man, I tell you what, at this point, when you see U is F composed of G, I don't really care what the question is going to ask. We're probably going to need the derivative. Whoops. U prime. The derivative is, okay, the derivative of f of something is f prime of something times the derivative of the something, the derivative of g. This is the definition of the chain rule. The derivative of f of g is f prime of g times g prime. And so if I want u prime of 1, well, we need f prime of g of 1. So there's the first thing I'll have to look up. What is g of 1 times g prime of 1? All right, so it looks like I'm only looking at the g graph right now. I need the value of g at 1. I need the slope of the tangent at 1. So g is this one right here. At x equals 1, we're looking at this point right here. So the value of the function, we see the scale on here, the value of the function, g of 1 is 3. And g prime of 1, well, let's see, it looks like we've got a pretty steep negative slope. I can count the squares because this is just a line, and looks like at that point we're going down 3 over 1, so it looks like my slope is -3. Again, looking at the location of the g graph at x equals 1, and then the slope of a tangent at x equals +1. So now we've got f prime of 3, g of 1 was 3, times -3. So now I need f prime of 3. So I'm going back to the graph. F prime of 3, 1, 2, 3. So it looks like we're looking at the derivative of the f graph, the slope of a tangent to the curve at that point. And here again, I'm counting squares. And I tried to draw this fairly accurately for what was in the book. It looked like it was going down 1 and over 4 before it crossed a grid line. So I'm going to say that my slope of a tangent at x equals 3 looks like it's about -1/4 to me. And it didn't look precise to me, but that's the idea. Using the graph to say the slope of a tangent to this curve, so to speak, is -1/4. And so -1/4 times -3 looks like my answer is +3/4. Using the graph, finding the location, as well as the slope of a tangent at different points. And there's some other parts. I think this was just part A or B or something like that. They also have G composed of F. I think they also had f composed of f or g composed of g. And I think for one of those questions, when you do it, at some point you're going to be trying to find the slope of a tangent line at a corner. And if that happens, the slope of a tangent at a corner just doesn't exist. And so the derivative of the composition doesn't exist either. And then I will finish up this little review video with a question like this, where they give you a graph. And I didn't copy a specific one. This might be similar to one of the ones that's on there. But basically, given the graph of a function, make a sketch of the derivative. And this was from the problems in 168. I think this came from 42 through 44, those types of problems. Let's see if I can get these both on my screen at the same time. Close enough. Focus. So the big idea here, my function is increasing really steeply, and then it levels off, and then it decreases for a while, levels off, increases. Some of those significant points are the places where the tangent line is horizontal. Looks like my derivative is going to be equal to 0 at that point. It'll be equal to 0 at that point, and equal to 0 at that point. And then in between these two places where the tangent line is horizontal, the slope is negative. Small at first, then more steep, then smaller, but negative. This graph is decreasing, which means the derivative is going to be negative. Fairly low values at first, and then getting to larger values. And then switching to positive. Slope of a tangent line is a positive small number, a little bit steeper, and then leveling off. So we'll have positive small, positive a little bigger, and then positive smaller. Past the 0, negative tangent line, negative slope of a tangent line, and getting larger and larger and larger. So maybe doing something about like that, going off the bottom of my screen. And then on the left side, large positive value, still positive but smaller, 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 getting smaller but still positive. And so probably something that looks about like that. And so I'm not using an equation. I'm not assuming this is a 4th degree and this is a 3rd degree, but that kind of ends up being what it looks like, doesn't it? Things that would be graded on a common exam when they've had questions like this in the past, it'll be like, where does it cross 0? Where is it positive? Where is it negative? Just general shape. It's not going to be a very precise thing, but just what is the general shape of a graph that is a derivative of a given graph. Okay, I am going to stop this video at this point. This one is long enough, but of course, come to the study sessions, or if you aren't able to do that, you can also contact me through email. Either way, good luck on the common exam, and I'll talk to you later. Bye-bye.